recording. Recording in progress.
Okay, good morning, Bitcoin blockchain course dudes. So, because you're so nice, I'm going to record multiple videos for you. I did not intend to do it, but you know, I have to be honest with you. But you're such an awesome group, and I really think you're an awesome group. So, I'm going to record some videos that will kind of summarize what we are doing in class. Okay. So the first thing we talked about in class, we talked about public key cryptography. You have a video on that, but we also talked about trees, and we didn't talk about trees that are growing in the forest, right? We talked about trees as a data structure. So this is a data structure, and this is basically the bulk of the data structure in computer science. Okay, so everything else, inside your computer is stored in this fashion, and I'm going to show how it is, and then I'm going to give you some examples. So for example, so what is a tree? A tree is basically a data structure. So it stores data, okay, with the following things, such that each node in this data structure has children. So symbolically, you can think about this data structure as being like this. This is your node. And now you have basically children. Now here you have 2 children for each one, at most 2 children. This is called binary tree. If you have more, it is going to be called like trinary tree, quarterly tree, etc., etc., etc. Okay? So each one has children. Now, if you don't have a child, it is called a leaf. So for node, you have children, and leaf if you don't have children. So for example, what kind of a structure, what kind of an example of in a computer science you have this for structure? For example, the folder system. So I have one big folder. This is your big folder. And then you have subfolders. Now you can have more subfolder or directories for each folder. For example, if you have a desktop or documents in Windows, underneath you have many subfolders. Okay, and usually you get lost in these subfolders, but that's a different story. So you have subfolder here, and then you have more subfolders here. Okay, so you see that you have a tree structure here. Now, in each subfolder, you may have files. So folders, underneath folders, you can have files, right? But files are somehow contained in this folder. So they are not part of the tree. They are kind of located inside this folder. So, it's a little bit different setup. But I think you get the idea. Now, why is it like useful? Why data structure like this useful? Because you can use it to do a lot of stuff in with the data in a very rapid way. For example, you have sorting algorithms using this. So I'm not going to formally define how the sorting algorithm works. I'm now just going to show how it works. So let's say you have a sequence of numbers, or letters, or not, or let's say, or names, or whatever. So let's say you have 1, -1, 2, 3, -5, 6, and you have, let's say, -10. Okay, and now you want to sort it. Now, if you have something like this, it's actually very easy to sort. You can just inspect it. But let's say you have billion of them. How do you do that? Okay, so for that, you can actually use a tree structure, and I'm going to show you how to do it. First step, you create a binary tree from this sequence. So how do you do that? Okay, let's say you have, so you draw a node and you put 1 here. And now you have -1, and -1 is less than 1, so it will go to the left of 1. Okay, so you create a child which is, which is -1. Now what about 2? So 1, you compare it with 1, right? And because 2 is greater than 1, it will go to the right-hand side. Now what about 3? Okay, so you start, you go in here with 3, and now you compare 3 with 1. So because 1 is less than 3, 3 will go to the right. But now you can see here that you have to compare it with 2 as well. So now you go and you create a new one, which is 3. Okay, so 3 is going to be a child of 2 and a grandchild of 1. Now you have -5. So you start with -5 here. You go to the left because 1 is bigger than -5. Now you compare it with -1. -1 is bigger than -5, so it goes to the left, and now there is nothing here, so you're going to create -5 here. Now what about 6? So you start with 6 again here, you go to the right, you go to the right, you go to the right, and then you compare it with 6, and you go here. Okay? And -10 is the same, and you are ending up of going here. So the idea of the algorithm, of this algorithm of creating these trees, that anything you compare it with a node. If it's going to be larger than what the value in the node that you compare with, you are going to go to the right. If it's going to be less, you are going to go to the left until you hit the earth, until you hit nil, and then you are going to put, you're going to create a new leaf or a new element of the tree. Okay? Now, how do you now, using this, it's very easy to sort. So it is called Depthfirst search. So you have something like this. You say print left, print node, print right. And how is it going to work? Well, you come here and the algorithm tells you print left. So first you need to print the left part. Then you want to print this, then you want to print the right part. Okay? So now you want to print the left part. Well, the left part is going to be -1, -5, -10. So -1, you go to -1, you still need to print the left. You go to -5, you need to print the left. You go to -10, and then you need to print -10. After you printed -10, you are coming here. Okay? So if you're coming here, it is going to be -5. So you are going to print -5. Then you are coming here, you are going to print -1. Then you are coming to 1. Okay, so you are printing 1, and now you want to print right. So you are going to print everything on this side. So it's going to be now you are going to print. Usually you go to the right, you have 2, but here you still need to do something. There is nothing here, right? So you have to first to print the node. So you will print 2. Now you still go to the right. Here you need to print 3. Okay, so you print 3 because there is nothing to the left. Let's say here there was something. Let's say it was 4 here. Then you would print 4, and then you would print 6. Okay? And you can see that you have an ordered sequence. So it's a very efficient way to store data because you can see that you can actually print it in an ordered fashion or sort it in an ordered fashion in a very efficient way. This algorithm is called basically is a manifestation of something which is called quicksort. Okay, and this is like one of the most famous algorithms in computer science in the 20th century that was invented, and essentially it is based on this methodology. Now, one thing to to observe about these trees. The first thing that this is kind of in some sense it's like a singular example, right? Why is it a singular example? Because when I discussed it with you here, I said that every node has up to two children. So in your mind, when you hear a professor or somebody tells you up to two children, you think that, if you have one child, it's an outlier. If you have two children, this is like the generic case. This is the usual case. Well, here you can see an example of a sequence where it is not the usual case. Here, okay, the case is that here you have it, that you have basically, the tree where you have only one child, except of one where you have two children, right, or two subtrees. Here you have only one child for each one. So 2 has only one child that goes to the right, which is 3, and 6 is going to be a child of 3. Now, this is going to be, now, also a huge advantage of this guy, okay, that as you sort it from in a ascending order, so here I go from the smaller to the largest, okay, I can actually also sort it in a descending order, okay? So how do I sort it in a descending order? It is going to be print right. So first you print the right side of the tree, then you print the node, and then you print the left side of the tree. So if you do it here, okay, first you need to print this, then you need to print this, and then you need to print this. So how will it work? Well, first you need to print right. So you go to the right. Well, you still have something on the right. You still, until you have 6, you hit 6, you have something on the right. So here, the first one you will print is going to be 6, then it is going to be 3, then it is going to be 2, because you always print right, then you print nodes. There is nothing on the left, so you don't print it. Then you have 2, then you print the node, which is 1, and then you start going here, right? So then you go and you will print, okay, so you have here, you print, you print -1, then you print right, nothing, you print left, you print -5, then you print -10, and you get the same sequence, but instead of getting the sequence in a ascending order, now you have it in a descending order. So you go from the larger to the smallest, okay? So this just shows you the power of this structure. The power of this structure, this is called, trees. Now, one additional way, one additional thing that we're going to discuss about trees are the Merkle trees, and we're going to do it in the next video. Okay, thank you, and have a great day.